Hello everyone and welcome. In today's video, I'm going to show you how to solve this projectile motion problem. Let's look at the problem. Water from a hose is directed towards a building. The water leaves the hose at a speed of 43 meters per second and at an angle of 43 degrees above the horizontal. The base of the hose is a horizontal distance d equals 43 meters away from the building. Find the height h where the water strikes the building. This is a nice problem and it will teach you a lot about how to solve projectile motion problem. Let's look at the solution. To solve any projectile motion, the first thing to do is to establish your coordinate system. Now, since this is a two-dimensional motion, we need to use the xy coordinate system to represent the vertical component of the motion with the vertical axis and also the horizontal component of the motion with the horizontal axis. So to do that, I'll first draw the xy coordinate axis. So the vertical axis, which is our y-axis, will represent the vertical component of the motion, whilst the horizontal axis is going to represent the horizontal component of the motion. With this, we can place our origin at this location. That is where the water leaves the hose, and we are told it does that with a speed of 43 meters per second but at an angle of 43 degrees above the horizontal. So if we start from the origin, this is the initial velocity vector which points in this direction because it makes an angle of theta with the horizontal. So this speed vector or velocity vector, let's call it v initial. That's the initial speed. This water is targeted at a building. So the target is a building and that building is located some distance d from the origin. That building is located here, okay? And then the building is the target, all right? So the goal is to calculate for the height at which the water strikes this building. So the height we need to calculate is going to be the vertical height h. So we need to find the height, that is this point where the water strikes this building. So with that, we know that for any projectile motion, once it is launched at an angle with the horizontal, it is going to undergo a parabolic path because as it is traveling, it travels a horizontal range at the same time as the vertical height. So with this, we are going to see that the trajectory of the water is going to be something like that, get to a maximum height until it strikes the building. This is another key thing to note in this problem. You are not to calculate the maximum height. We are interested in calculating the height where the water strikes this building, all right? So that happens at the same time the water travels this range. So the time is key in determining or solving this problem. But we still need to do something. And that thing is to resolve this initial speed in its horizontal and vertical component. So we have a vector which makes an angle theta with the horizontal. Then that vector is going to have a vertical component which is along the vertical direction, as well as a horizontal component which is along the x-axis. So to do this, we need to resolve this vector vi into its vertical and horizontal component. So the vertical component in the y direction is going to be vi y, and in the horizontal direction or x direction is going to be vi x. So here we can see we have a right triangle with the opposite being viy and the adjacent being vix. So we can apply SOHCAHTOA to determine viy and vix. So viy being the opposite, we will have it to be viy equals vi times the sine of the angle, all right? In the same sense, vix is the adjacent, so it's going to be vi cosine of the angle, all right? So now we have resolved the initial velocity into its component. This is important because we need to treat each component separately. even though they occur at the same time. So let's look at the data we have from this problem. What is the information given to us? So first we are told that the initial speed vi is 43 meters per second. We are also told that the angle it makes with the horizontal is 43 degrees. Also, the distance, which is delta x, the distance we are told is 43 meters. Another important thing to note is that we are to take acceleration of free fall to be 9.8 meters per second squared. Also, we are neglecting air resistance. So forces due to air resistance is 0. With this, we are now ready to solve the problem. The first line of attack is that we are looking for some vertical height. So we need to consider the vertical displacement equation in kinematics. So that equation says that the vertical displacement traveled at any time is given by the initial vertical speed times the time minus 1/2 g, that's the acceleration of free fall, t, that's the time, squared. If we use this equation, this delta y with our origin being the 0 and that vertical height we are looking for is here. So delta y is y final minus y initial equals viy times time minus 1/2 g t squared. That is the importance of our coordinate system. So it tells you where what is and in what direction what is. Okay, so yi is the initial vertical position of this projectile or the water, which is 0. Okay, and then the y final is going to be that distance at this point or the position at this point, and that gives us some distance h. So y final is going to be h minus 0, so that is h is equal to viy, that is the initial vertical speed, times time minus 1/2 gt squared. And we are looking for this h on the left hand side of the equation. And if you look at this equation carefully, it depends on some time t, which we don't know at this point. And this is the neat trick about projectile motion. We can use the horizontal component of the motion to find information about the time, and then that will help us find that particular height where this happens. Why? Because we are given the horizontal distance traveled, d, and also we know the initial speed of this object in the horizontal direction, and that the physics says the horizontal speed remains a constant, right? As the object is traveling horizontally, the speed remains constant. Why? Because 1, acceleration due to free fall does not act horizontally on this water. Secondly, remember we neglected air resistance, so that is 0, so the speed of the horizontal motion is not affected. So with that key information, we can find the time. So to find the time, we consider the horizontal displacement, so which is delta x is equal to vix, the initial speed in the x direction, times the time. So to find the time, we divide both sides by vix. We divide the left hand side by vix, and this, so the vix divided by vix cancels out to 1. So 1 times t just gives us that time. So now the time is going to be t is equal to delta x divided by vix. However, vix is not vi, but vi cosine of theta. So we need to insert that here. So vi cosine of theta. And you need to always check that you are not just using vi, because for the horizontal component, we need to use the horizontal component of the initial speed. So that gives us the initial speed in the horizontal component. So doing this T would be equal to delta x, which is d, all right, and that is given to us, divided by VI cosine theta, so VI cosine of theta. So that d is given to us as 43 meters, and then we divide by VI, which is 43 cosine of 43, and that is in meters per second. So if we divide that by that, we should have 1.4 seconds. So it's going to take the water 1.4 seconds to travel that horizontal distance d. And at that same time is the height where the water strikes the building occurs. You see how neat that is? So the time is an important factor that connects the two components of the motion together. So if you need that information for either of those components, you can use the information you have from either of those components to solve the other. All right, so now we found the time to be 1.4 seconds. Now we can find the height h. So let's do that. So now to find the height, we go back to h equals VIYT minus 1/2 GT squared. So we found the time to be t equals 1.4 seconds, and now we can use it to find the height h. So the height h is going to be VIYT, remember, not VI, but VIY, which we found to be VI sine of theta. So we have VI sine of the angle theta into brackets, multiplying the time, which we just found, minus 1/2 GT squared. H equals 43 sine of 43 times the time, which is 1.4 seconds. So minus 0.5 times 9.8, then times the time, which is 1.4 seconds also squared. So simplifying this will give us the height to be equal to 31.4 meters. So therefore the height is equal to 31 meters. All right, so this is the height that occurs just at the same time as the horizontal distance travel at this location. So that height is about 31 meters, and that brings us to the end of this video. So if you are new to this channel and you found this very useful or helpful, please give us a thumbs up and also subscribe if you've not done so already. If you are already a member, thank you so much. Give a thumbs up and let's keep doing physics. Until then, I will see you in my next video. Bye bye.